Acid rain, increasing levels of greenhouse gases, contaminated waterways, polluted cities, a depleted ozone layer. This list can go on and on. Whereas our world in the 21st century has experienced a great number of advancements in everything from agriculture to commercial products to medicine, it has also been negatively impacted by the fruits of its labor, which is where green chemistry comes in. My name is Massiel Morel, and after this presentation, you will hopefully be leaving with a better understanding of sustainability in chemistry, a science that drives our being and dictates the future of our world. Now, we will start off with an overview of what green chemistry is and where it originated from. A more in-depth analysis of this field will follow, coupled with several examples of the most useful applications of green chemistry. And finally, we will conclude by summarizing the extensive reach of green chemistry and its impact on the outlook of science. So we've talked about this green chemistry, but what really is it? Well, according to the US Environmental Protection Agency, green chemistry concerns itself with the design of chemical products and processes to reduce or eliminate the use or generation of hazardous substances. It applies this across the life cycle of a chemical product, going from its design and manufacturing to its use and ultimate disposal. At its core, green chemistry is a multidisciplinary field that pulls in from more than one specific area. It looks at the prevention of pollution at the molecular level, at the reduction of the negative consequences of chemical processes and products on human health and the environment, how to design new products to pose the least amount of intrinsic hazards, and the elimination of existing dangers within the products that already are on the market and in constant use. And just from this overview alone, we can see that green chemistry is an all-encompassing field concerning itself with more than just the hazards that arise from chemical toxicity. It looks at energy conservation, waste reduction, and designing for the end life of a product. But how did it all come together? Where did this field that could potentially change the world as we know it come from? What is its history? Well, it started in the 1960s as Rachel Carson changed the meaning of environmental protection as we know it. She wrote the mainstream scientific book Silent Spring in 1962, which outlined the devastation that certain chemicals had on local ecosystems. It was a wake-up call that the public and scientists all alike needed. It laid the groundwork for the environmental movement that to this day still persists. By the 1970s, President Nixon established the EPA. And then in the 1980s, the chemical industry and the EPA focused mainly on pollution cleanup. But then the foundations for green chemistry really set in during the 1990s, when scientists began to look at the overall prevention of pollution from its source, with the Pollution Prevention Act of 1990 marking an unmistakable policy change from pollution control to pollution prevention. Now, by the 2000s, green chemistry had already been coined as a term. Nobel Prizes in this field were won, which further increased the awareness among scientists that the future should be green. And even now, green chemistry has more to give. The future lies on green chemists and engineers working to take their research and innovations from the lab and into the boardroom through the creation of viable industrial products that can be embraced by the industry leaders of tomorrow. Now, what really differentiates green chemistry from regular pollution cleanup, which is otherwise known as remediation, is its philosophy to stop creating pollution in the first place. It tackles it head front, resulting in what is known as the source reduction, where the generation of pollution stopped altogether by eliminating rather than simply treating and reacting to the hazards of reagents, solvents, raw materials, and products. Now, this leads us to the essence of green chemistry, with the 12 design principles that Paul Anastas and John Warner came up with. Now, beginning with prevention and ending with safer chemistry for accident prevention, green chemistry and its founding notions come full circle. As atom economy should be maximized by chemical reactions, chemical synthesis should pose little to no toxicity concerns for one's health and environment. Safer chemicals should be designed to perform their expected function with no toxicity, while solvents, separation agents, and other auxiliary substances should be avoided and harmless if used. Energy efficiency should be increased, just how renewable feedstock or raw material should always be used. Derivations, such as blocking groups and temporary physical or chemical processes, should be avoided altogether in order to minimize the amount of reagents used and thereby the amount of waste produced. On the other hand, catalysts such as zeolites should replace stoichiometric reagents since catalysts can easily control reaction pathways, reducing unwanted side products, generating better atom economy, and lowering energy demands. Products should also be designed for innocuous degradation that doesn't persist in the environment. And ultimately, analytical strategies need to be further developed to allow for real-time monitoring that is prior to the formation of hazardous substances. And green chemistry, as evidenced, is an overwhelming technical field that has a lot of information available, which makes it very complex and extensive. The first two principles of green chemistry alone have their own systems in place that can be further broken down. With prevention, which is the first design principle, the idea is that it's better to prevent waste than it is to clean it up after it's already been created. One perfect example of this is the old way of manufacturing phenol, which is found in the mouthwash, disinfectants, and nylon manufacturing. The chemical equation shows that 1 mole of benzene yields 1 mole of phenol. Its yield in practice is approximately 82%, which is relatively good. However, this calculation obscures the fact that the reaction also generates 1 mole of sodium sulfite for each mole of phenol produced. This can present a serious problem of waste management and add significantly to the cost if sodium sulfite is not in demand. Now, atom economy also steps in as an alternative measure to yield. It is the second design principle of green chemistry, and it upholds that synthetic methods should be designed to maximize the conversion of all materials used in the initial the process to the final useful products. It can be calculated by dividing the relative molecular mass of the desired products by the relative molecular mass of all the reactants, and then multiplying by 100%. The closer the calculated value is to 100, the less the waste there will be. It's also important to note that some reactions that have 100% atom economy can also have poor yields. So it's necessary to consider both measures of efficiency, yield, and atom economy. Now, when analyzed in all its entirety, green chemistry has already left its mark in the world and has the potential to keep doing it in the future. Some of its most recognized successes include the reduction of formaldehyde, which can have adverse effects on one's health after long periods of exposure, the elimination of ozone-depleting chlorofluorocarbons, the development of sustainable technologies for farming, and the reduction of dyes in manufacturing, which, if not minimized, can pose great risk to aquatic life via its absorption and reflection into the water. Now, we've already taken numerous steps to have a greener world in the present moment. We have developed a method for computer chip preparation that uses supercritical carbon dioxide in order to significantly reduce the quantities of chemicals, energy, and water used for the production of those chips. Medicine is also not staying behind, with the drug simvastatin being synthesized via an engineered enzyme and a low-cost feedstock. Even oil-based paints, which usually give off large amounts of volatile organic compounds, they're being revolutionized. Companies have created a mixture of soya oils and sugar that replaces the fossil fuel-derived paints and resins and solvents, which cuts down on the hazardous volatiles by at least 50%. In essence, though, the acceptance that the chemical industry must not adversely affect the environment for future generations, that's what drives the development of green chemistry. We saw that this is not a separate branch of chemistry, but rather an approach that permeates every stage of process development. Simply put, its aspirations can be summed up by the word sustainability. And even then, this field has developed rather rapidly in the last 30 years, and it's still at its earliest stages. Promoting green chemistry is a long-term task, and many challenging scientific and technological issues need to be further resolved. Scientists, engineers, industrialists, they all must work together to promote the development of this field, as there is no doubt that the implementation of green chemistry will contribute greatly to the sustainable development of a greener society. Now, this concludes my presentation, where the following slide will contain all the references used. Now, thank you for listening, and may the future be as green as it can be.